Hello everyone, welcome to this lecture on Boolean Algebra. This is a fundamental concept that powers modern computers, digital electronics, and all logic-based systems. This topic lies at the heart of computer organization, digital circuit design, and decision-making in software logic. Now let's begin with a deeper understanding of its origin and significance. In the 19th century, an English mathematician named George Boole developed a new branch of mathematics to model logical thinking using symbols and equations. His central question was, can human reasoning be expressed mathematically? His answer formed the foundation of Boolean algebra, a system where variables only have two possible values. It's either true or false, represented true by 1 and false by 0 in computing. This binary system allowed logic problems to be expressed in a formal mathematical way. The impact of this was far-reaching, laying the groundwork for logic control systems, digital logic, and eventually the structure of computer processors. Now let's draw a clearer comparison here. In traditional algebra operates on real numbers like 9, 15, or 996. But the Boolean algebra operates on binary values. It is either 0 or 1, right? A or B. The traditional algebra uses arithmetic operations like plus, minus, and for example modulus, and so on and so forth. But the Boolean algebra uses logical operations, for example and, or, not, and this goes on. In traditional algebra we have infinite values allowed. Like you can combine, for example, 9, 9, 9, 5, 3, 2, 4, or 6, 7, and this is infinite basically. And in Boolean algebra you can use only two possible values. It is either true or false. In computer we call true 1 and false 0, but for example in your own logic you can call the true T or F, A or B. Yeah, you get the logic here. You can only have two values which can represent either true or false. And result is what? In the traditional algebra, the result is a numerical computation. And in Boolean algebra, the result is logical decision. As a beginner in Boolean logic, first we will learn about and, or, and not. And returns 1 only when both inputs are 1. So 1 and 1 equals 1, or 1 and 0 equals 0. It will only return 1 if at least one or both inputs are 1. But in OR, returns 1 if at least one input is 1. So if we have 0 and 1, we have 1. If we have 0 and 0, we have 0. And the NOT inverts the input, turning 1 into 0 and 0 into 1. So NOT 1 equals 0, or NOT 0 equals what? 1. Now, Boolean algebra provides a compact and efficient way to represent truth conditions that occur frequently in programming, hardware control, and logical automation. So this was just the beginning to meet you with what you will learn in this section of our course. We will explain these conditions and values more deeply and detailed in next lectures. So don't worry. Hello everyone, I'm Typhoon here again, and in this lecture we are going to explore the basic Boolean operators, the AND, OR, and NOT. These are fundamental tools in digital logic, and they are used in nearly every electronic device you can think of, from computers and smartphones to microwaves and traffic lights. If you're just getting started with a computer organization or digital systems, understanding these operators is your first big step, and I will get you through each concept, explain how it works, show you the symbols, provide truth tables, and walk you through how it is implemented in an actual electronic circuits. So what is a Boolean operator? A Boolean operator is a special kind of function that works on one or two binary values. Binary values are simply 0 or 1, where 0 usually means false or off, and 1 usually means true or on. Now, the values that Boolean operators act on are called operands, and the result is also either 0 or 1. Now, Boolean operators are essential act on are called operands. So, to make things clearer, we will use truth tables. A truth table is a tool used to show how the output of a logic operation changes based on all possible combination of inputs. But before we jump into the operators themselves, let's warm up with a real-world example from binary arithmetic. So, the truth table example we will do here is we will create x, y, and we will also have carry, and we will have sum here. So let's draw the lines here. 1. And now we have the two binary values, x and y, and add them. When you add binary numbers, there are two things to think about. The sum we have here, this is the result of the addition, and we have the carry here. If both bits are 1, we carry a value to the next position. Now here's how the result looks in a truth table. So here we will have 0 and 0. We have 0 carry as well, and the sum is what? The 0. We have 0, 1, 0, 1. We have 0 carry, but the sum is 1 because of y is 1 here. Or else we have 1 and 0, again same. But if you have two 1s, we will have another carry, and the sum is gonna 0. But we'll have just a small one here, which we will not talk about that right now. Now this is how binary addition works inside a digital circuit, and now every row shows one possible input combination and what the circuit should output in that case. And this, as you can see, if we have both 1s, we will have the sum of 0. Now we will return to binary addition later when we design circuits called adders, but for now let's look at the core logic operations. Logic gates are physical electronic components that perform Boolean operations. Now think of them as a small building blocks inside the computer's processor. Now each type of logic gate has a unique shape and behavior, and it performs one specific logic function like AND, OR, NOT. And in the next lectures we'll cover each operator in detail, including its definition, the truth table, and the circuit symbol. But now we will start with the AND. So we have the AND operator, also called the conjunction. The type is binary operator. All of these are binary operators. How we can tell that it's a binary operator? Because it uses two inputs. It's either 1 or 0. So it's a binary operator. And the symbols are this. Now this is a common in logic and also common in programming, is this one, just a dot. Or you can also just write AND. This is a symbols of ANDs here, right? The output rule is the output is 1 only if both inputs are 1. So let's do another example here. We have a, b value, and we have x, and we have a and b. So what we will have here, we will just 2, 3, and 4. So if we have a0 and b0, we will get 0. If we have a0, b1, we will get 0. If we have a1, b0, we will get 0 again. But if we have a1, b1, we will get 1. Now this is how AND operator works. So imagine two switches connected to the light. The light turns on only if both switches are on. Or for example, like this is a light bulb. Here we have two switches and this is battery, right? This is just how AND works. And if you are designing computer circuits, AND has a circuit here. So for example, X and Y, the circuit here is what? Now this is a circuit of AND operated. Now this is how you represent AND in circuits here. Now the gate is shaped like D, as you can see here. Now the behavior is similar to multiplication in regular math, which is 1 by 1 equals 1. Remember, this is just like that. And all other combinations are 0 here as well, but just this one. And we also have the OR operator, also called as disjunction. The type is binary operator as well. The symbols is V in logic, plus in math, or just OR in programming. The rule is output is 1 if at least one input is 1. For example, we have A, B, and X, or A or B. So if we have A0 and B0, we will have what? 0. If we have A0, B1, we will have 1. If we have A1 and B0, we will have 1. If we have A1, B1, we will have 1 as well. Now you can see we got 3 and just 1 0 here. Now think of the two doors that lead to the same room. If either door is open, you can enter. Now that's how OR works. And how you represent OR in logic is X, Y, for example. And this is how you represent OR in circuits. Now the gate has a curved shape. It behaves like an addition, as we mentioned here. 0 plus 1 is 1, and 1 plus 1 is still 1. So we don't carry anything in the Boolean logic. Now we have the NOT operator. Now I would say that NOT operator is easiest among these. Now the NOT operator, also called negation, is represented in a unary operator. It uses only one input. The symbols are this in logic, and often for like X, or a line above the variable. Now the rule is basically output the opposite of the input if A is 1 and not A is 0, and vice versa. So basically how we can write that is we will just have 2. So we have A here and we have not A. This is so easy here. So if A is 0, not A will be 1. And if A is 1, the not A will be 0. That's it. The NOT operator is like a mirror that always shows the opposite of what it says. If the input is true, the output is false. If the input is false, the output is true. This reversal process is known as inversion, and it's why the NOT gate is also called an inverter. Now let's use a practical analogy. Imagine you are looking at the room with a smart light bulb. The switch on the wall is programmed with a NOT logic. If the switch detects the signal off, it turns the light on. If the switch detects the signal on, it turns the light off. Now this behavior is especially useful in logic circuits when you need to deny or cancel a condition. For example, a security system might activate an alarm only when a sensor signal is not triggered. So in programming, in many programming languages, the NOT operation is written using this ternary symbol. So basically not true equals false, and not false equals true. And in circuits, the NOT gate is drawn as a triangle like this. For example, A, or let's actually represent it by X. Here, triangle, circle, and what? NOT X. Now, that is how you draw in a logic circuits. The triangle represents the flow of logic, and the circle means invert the input. Now you will encounter NOT gates frequently when designing logic functions that require cancellation, inversion, or toggling a state from on to off. Now George Boole used multiplication for and addition for or. Why? Because their behavior is similar to arithmetic, and using symbols made the system easier to work with. This idea connected logic to mathematics, allowing logic statements to be multiplied like equations. Now that you know the basic logic operations, you will soon learn how to combine them to build more advanced logic gate, like with XORs, which is exclusive OR, true only when one input is true, not both. You will learn that in next lectures. And we have also NAND or NOR. These are the combinations of basic operators. Now you will also learn how these gates are wired together to create a circuit that can add, subtract, compare, and store information. Now the way things your computer does every second here. Take your time to review the truth tables and practice drawing the gate symbols. This will help you build a strong foundation as we go further into digital logic. Thank you for watching. I'm Typhoon, and I'm meeting you in the next lecture.